All right then. So the intermediate value theorem. Okay. So let me talk about the intermediate value theorem. It's very basic. Okay. This is very. It's almost not even needed to be explained. Okay. It's almost like obvious stuff. Okay, from what you've been learning. But what you need to know in advanced math as we move through some of the things that we've been assuming or using without even thinking about it, some of these concepts actually are formally stated as theorems. Some of these theorems are tricky to understand. Some of them are really easy. So the intermediate value theorem, let's just take a quick look at this word. First of all, intermediate means in between, right? It's like an intermediate step would be some step between the beginning and the end. So it's something in between. And of course, we're talking about a value. So a value in between. So what I'm going to do is I'm going to draw you a little diagram first, and you can draw this in your notes. Okay, I will have a formal definition coming up. But let's say that we have some function like this, all right? And this function is, try to hit that button, intermediate value theorem. So the function is not defined, it's just f of x, but what we do know about it is that it is continuous. Okay, so in these theorems, in order for these theorems to be applied, there has to be some hypotheses that are met or criteria that are met. So this is a hypothesis here, okay? If the function is continuous, which this one is, so for all continuous functions, okay, what this is saying is that if there is a certain value right here, okay, so let's say this is value y1 for value x1, the function is continuous. So if I take another value y anywhere else, and I'm going to pick this one over here. So here's y2, and this corresponds with x2, all right? So what the intermediate value theorem states is that between these 2 points right here, if this line is drawn and there's no gaps or discontinuities, there's no asymptotes, okay? If it's continuous, it doesn't even have to be differentiable, it just has to be continuous. And I'll talk more about, what differentiable is. We'll talk more about that soon, coming up here even today maybe. But if it's continuous, and there is a value, so let's call this value, let's say w, that is right here, okay, in between y1 and y2. So if there's a value intermediate in between y1 and y2, it means that there must be a value here, c, let's say, that is between x1 and x2. Okay? It's kind of like saying if you are walking from school home, do any of you walk home? Any of you walk home? Anybody, you live close enough to walk home? You used to. Okay. So let's say you walk home from here. You're walking home. Even if it's a long ways away, it doesn't matter. But you start at the school and you end up at home. Okay? That means that if you are to be found somewhere in between here and home at a certain point, like this, at a certain point between here and home, that means that you must have reached that point sometime after you started and sometime before you arrived. If you were found at a point in between school and home, then that means that you would have gotten there at some point between when you started and when you arrived. Okay? That means that because it's continuous, if there's an intermediate value for y, there must be a corresponding value for x that meets up with that. Okay? Let's put that a little more formally now. Okay, so you can write down some of this if you want. Here's another graph. Okay, that's a nice informal looking graph. You don't have to copy all that down, but this is a lot of what I already just stated. So the curve of the function, if the curve is y equals f of x, okay, so that's the blue graph, is y equals f of x, that is continuous. And of course, we describe an interval between a and b, so that would be from some point here to some point here. If it's continuous, at least on this interval, we can focus on this interval then. And if we say w is a number between f of a and f of b, so that was our y1 and y2, remember, in our first example. So if there's a value between f of a and f of b, then there must be a value c that's between a and b. So it's basically defining the nature of continuous almost. Like this is what continuous is. There's always a point in between, these values. There's always going to be a point somewhere where you're going to connect these values. If it's a continuous function, there's going to be a point somewhere in between that's going to have an x that's associated with it. Okay? And like I say, some of these theorems, it's like, why do we even bother to formally write this out? Well, it's something that we maybe take for granted with a lot of our calculations, but nevertheless, it is important for us to understand that this is a law, this is a rule. Okay? Okay, so now I'm going to expand on this a little bit. When I say here that there is a number, okay, a value c, well, there's actually at least one value c. There could be more than one value of c. For example, between f of a and f of b, if the function f of x is continuous on a to b, and there is a value w exists between a and b, there must be at least one value for c between a and b, but there could be more. Notice that this f of x is still a function. It does not violate the vertical line test, right? But here we have one c, two c's, three c's that have this same value. So there could be more than one point. It has to be at least one. Okay, just backing up, if there wasn't one, it would have to be discontinuous, right? It would have to be a gap. So at some, here's y2, okay, let's say this is y1. If this value w here, okay, it doesn't look to be on there, there's no x that corresponds, well, that's because it's not continuous, right? So w is between y1 and y2, but because it's not continuous, the theorem doesn't hold. You can't invoke this theorem, okay? So it has to be continuous. Okay? Any questions so far? Yeah. Yes. Okay, so let's expand on this a bit. Let's say we have the walking home from school example. Okay, you walk home from school, you're walking home, and then you realize when you get to this point right here, you're almost home, but oh my goodness, it's wintertime and I dropped my glove. I dropped my glove in the snow somewhere, so I got to go back and look for it, and oh, here it is. Okay, good. I grabbed it, turned around, and I'm going home again. And then I actually take a wrong turn. I forget where home is. I go past home, and then I come back. That's what this graph is saying. So this point W right here, you actually passed that point 3 times because you went past it, forgot your glove, came back, passed it a second time, found your glove, and then went home and passed it a third time. So that would be an example where there's at least one. Okay, so if this is let's say this is a certain distance from school to home, and you jump over a sidewalk or something, and you say, hey, the sidewalk is between home and school, but I was never there. Well, that's because you jumped over, so it's discontinuous. You see, you're walking every spot, and then you jump over, and let's say that means that you skip a spot. Well, then it's not continuous. Then this theorem does not apply over the entire interval. It only works for continuous intervals, but you can have more than one. Okay, let's just take a moment, say how is this useful? Okay, one algebraic reason why this is useful is this. So whenever we can show that, okay, so how is this useful? When there is one point above some line, a point above some, let's say horizontal line, and a point below the same horizontal line, and the curve is continuous, we can do things like this. We can prove that there would be, let's say, an intercept, an x-intercept. Okay, so here's an example. Is there a solution? I want to write this down so we can do this. You have this as an example. Is there a solution to x to the 5 minus 2x to the 3 minus 2 equals 0? Okay, if you remember what a solution is, we're looking for a root or roots. Right? That's what we're looking for. Okay, well, this is all we're given between 0 and 2. So I tell you what we're going to do is we're going to, first of all, notice that this is a polynomial. this part right here, this is a polynomial. And so that means by nature, if we were to graph it, it would be continuous. So this is continuous. All polynomial functions are continuous. We have a problem if there's 1 over x minus 2, if it's rational, right? We have a problem if it is, root x minus 2. That's a problem. There might be a restriction there, okay, on the domain. So on any interval, though, a polynomial, if it's just to the power, x to the power of whatever minus x to the power of whatever, these are always continuous, okay? So polynomial functions are always continuous. So we got that figured out. And so what I'm going to do is I'm going to find out what the value of 0 plugged in here is and what the value of 2 plugged in here is. Let's see what happens. So 0 to the 5 minus 2 times 0 cubed minus 2. Okay. So let's see what this is. That's 0 minus 0 minus 2. So that's equal to negative 2. Okay. So x equals 0. You could say that y equals negative 2. Okay. So we do have, here's negative 2. At some point here, x equals 0, we have negative 2 as an intercept. Are you okay with that? Okay, what about now if we take a look at x equals positive 2? So positive 2, or we did 0 before, let's do positive 2. So 2 to the 5th minus 2 times 2 cubed minus 2. Okay, so what's this? 2 to the 5 is 32. Minus 2 times 8, 16 is 16. Minus 2 is 14. Oh, 14. Okay, so that means that over here on x equals 2, then the value is way up here at 14. Oh, interesting. So I have a point down here and a point here. Is there a solution to this equation, which means I'm actually looking, is there a root? Another thing, another way to put that, is there an x-intercept over this interval from 0 to 2? From 0 to 2. Well, it's a continuous function. So that means no matter what it does, I mean, if it goes up and down and sideways and left and right, there has to be at least one root. So by the intermediate value theorem, there must be a solution between 0 and 2. We don't know what it is right now, but we know there must be a solution. So the answer to this is by the intermediate value theorem, and you can read that IVT right now. By IVT, there must be at least one root between x equals 0 and x equals 2 for the function, for the equation given. Okay, so here is that equation. Here's that equation graphed. Now this is the corresponding function, y equals, right? But if you put 0 equals in there, then that becomes an algebraic expression, so that's not going to work. You're not going to be able to see the graph. But if you drew the corresponding graph to that equation, then this is what it would look like. And of course, the answer to this graph equaling 0 would be, is there an x-intercept? And yeah, there is. There's one right here. Okay, because there's negative 2. And then positive 14 would be up here somewhere. You see that? 14, 0, and wait, 2, or what? 2 and 13 minus, did I write that down right? Is 14 the right number here? It should be x equals 2. Doesn't look like it's 14. X to the 5th. Okay, this has got to be minus. There we go. Okay, so it actually looks like this, guys. There we go. So minus, I put a plus there. This is a minus. Nobody corrected me? You guys awake? What's going on? Okay, so anyway, so this is what the graph looks like. Here is my intercept right here. And then at 2, Yeah, the value should be 14 right here, eh? 214. Okay, if I can get to it. 214. Yeah, there we go. So because of those two values here and here, there's at least one intercept. That's true. Okay, got it? Well, here's 0, -2, and then 2, +14 is way up here.
So
214,
the
right there.
is
Well, the root is the intercept. Yeah, the root is the intercept. Okay. All right. There are other, here, let me just go, I don't think I have it on this. I don't have it on this computer, but there are other, okay, so this is on mathisfun.com, and here's an interesting thing. How do you use this? So, I'll give you 3 examples. An intermediate value theorem can fix a wobbly table. Okay, let's say your table is wobbly because of uneven ground. If you just rotate it, continue to rotate it, you'll find some point where all 4 will touch the ground. Because the ground itself is continuous. So if all 3 legs are on the ground, the 4th is the one that's in trouble. So as long as you rotate the 3 so the 3 make contact, the ground is continuous and it won't be decreasing, the ground won't be getting lower the whole time you spin it. It'll have to come up sometime, right? So you just keep spinning it and you'll get all 4 on there eventually. So again, there's always a point. There's always a point because the floor would be continuous. An uneven floor even would be continuous. Yeah, that's kind of cool. Another one. If you take a round trip somewhere, so you walk from here to home and back, and obviously home and everywhere in between is not all at the same elevation, let's say. So if you walk from here to home and back, because your trip is continuous, there will be some point where you will hit the point that's between the point you started and the point where you were the furthest away or whatever. At some point you will be higher than when you started. At another point you'll be lower than when you started. Okay? Unless you actually started at the lowest point or started at the highest point. But there will always be some fluctuation. It will always be continuous. Okay? That's another one. Finally, a third one. If you follow a circular path, somewhere on that circle there will be points that are directly opposite each other and at the same height. So treat this as a round trip, a literal round trip. If you walk in a circle, no matter what the heights are, okay, no matter what the heights are, at some point, you'll be able to draw a line across, and seems a little counterintuitive, but you'll be able to draw a line across from this elevation across the middle to the same elevation at some point there. At some point. Because if this is getting higher on this side, somewhere around here would have to be getting lower, and at some point it would be the same. So maybe when you're bored this weekend, you can walk around in circles and see if you can find a point on the other side of the circle that's exactly the same height and prove this theorem to be true. Wouldn't that be fun? Lots of snow on the ground, so maybe that would be a fun activity.